Morning, everybody. We're going to continue our unit on sequences and series today. And last class, we had the opportunity to look at sequences in general, as well as arithmetic sequences, which were sequences that either added or subtracted the same thing every single time. And so today what we're going to look at is we're going to look at something called a geometric sequence, which is when you are multiplying by a constant term each time. So you can multiply it, or if you want to think of multiplying with a fraction as division, you can do that as well. And so instead of a common difference, we have what's called a common ratio. We denote this here with the variable r, and this is the number that we multiply by to get to the number in the next sequence. And so like the way that you calculate that number, if we're multiplying by r each time here, we're saying times r to get from A to B, to get from B to C, we multiply by r. The way that we calculate what that value of r is that we divide a term by the term right before it. So we could figure r out by doing b divided by a. We could also figure that out by doing c divided by b, and so forth. D divided by c, e divided by d, and so on and so forth. And the reason that these are called geometric sequences, it's related to the geometric mean, which this is just the equation for a geometric mean. We don't really use that a whole lot in this course, but just to provide a little insight. And so the way that you're going to see a geometric sequence written, so we're still going to call the first term, like what we did with arithmetics, we're going to call the first term u sub 1, and we find terms by multiplying u sub 1 by the common ratio, which is r. So like if I wanted to get the second term, I would multiply the first term times whatever it was. So if the ratio is 2, I'd take the first term and multiply it by 2. If I wanted to get the third term, I'd take the first term and I would multiply it by 2, and then I would multiply it by 2 again, whatever the ratio is twice. And to get the fourth term, we would do the ratio 3 times the first term. And so a general pattern you can see here: for the second, you do r once; for the third, you do r twice; for the fourth, you do r 3 times. And as a general rule, the explicit formula here, to get any term, you're going to do the first term here multiplied by r to the n minus 1 power. So whatever n is here, you're going to multiply it by r n minus 1 times. And so this right here is our explicit definition, our general formula for this. And so we're going to look at some examples with geometrics to kind of start off and get us comfortable, and then we'll move into a couple of more advanced examples and go from there. So the first thing that we're going to do, we've got the sequence here. It goes 8, 4, 2, 1, 1/2. So we're showing that this sequence here is geometric. And so the way that we're going to do this, we're going to start with 4. So 4 divided by 8. So let's see, that can reduce to 1/2. So then I'm going to do 2 and divide it by the term right before it, divided by 4. 2 divided by 4 equals 1/2. That's how we solve for r here. 1 divided by 2 just equals 1/2. 1/2 divided by 1, anything divided by 1 is just itself. And so the common ratio here that we're dividing by, or multiplying by rather, is 1/2. And you may look at that and say, wait a second, Mr. Price, that is being divided by 2, man. Well, multiplying by 1/2 is the same thing as dividing by 2. So when we talk about geometric sequences, we're really only going to be talking about them in terms of multiplying. But they can, but you could also define that as division, but you're going to see it notated as multiplication. So then, if we want to find the general term u sub n, we want to write a formula that will let us find any number term here. What we're going to do is we're going to say u sub n. So we're going to borrow from this guy up here is the first term, which is 8. And then to get any term that we want, we're going to take this r. So we're going to do 8 times 1/2 to the n minus 1. And this right here is set up as a formula now, so where if I want to figure out a term number, I can just fill in for n. So like, for example, if I wanted to find the 12th term for this right here, what I would have to do is say, okay, I want to find u sub 12. We know that the first term is 8, and if I'm going to find the 8th or the 12th term here, I'm going to have to multiply by 1/2 11 times here. I'm going to have to multiply by 1/2 11 times. So I'm going to bust out my calculator here real quick. And I'm going to say, all right, 8 times 1/2 to the 11th. And it is approximately 0.00390, just rounding to 3 sig figs there. I guess 3.00391 rather, but it wants it as a fraction. So a quick thing to get something as a fraction, if you hit math right there and go to fraction and then just hit enter, it will represent that number, if possible, as a fraction. So the 12th term here is going to be 1/256. And so we're going to be doing a lot of stuff on the calculator today. So I would make sure that you have a calculator around, or if you need to get one, the app on the phone like Mr. Price has got here, you can do that. We are going to be doing a lot of things on the calculator. So make sure you have that handy. So then the next thing that we're going to look at, we're just going to practice some general algebra here, some general algebra skills with these. So you'll recognize this from the last section. So we want to find some values of k so that these terms are going to make a consecutive geometric sequence. So if we list these numbers out, they are such that if we multiply by r, whatever r is, times r, that we're going to get that there's this pattern of multiplying by the same number. So what we've got to do is say, okay, how do I figure that r out? What was Mr. Price talking about earlier? So the way that you find it, if I know this times r is going to give me 2k, the way that I'm going to solve for r here is I'm going to do 2k divided by k minus 1. And over here, to get from 2k times r to 21 minus k, the way that I find what r is I divide 21 minus k by the term right before it, divided by 2k. And what we can do now, we know r is equal to this. We know r is equal to this as well. We can actually set these two things equal to each other because we know that that is what our rate is. So we've got 2k over k minus 1 equals 21 minus k over 2k. And a common thing, when you've got a fraction equal to a fraction, you've got to multiply both sides by the denominators. But the shortcut way that you were probably taught was to cross multiply. Because if I multiply both sides by k minus 1, that's going to cancel out on this side. And if I multiply by 2k on both sides, that's going to cancel out here. And so the shortcut way that you were probably taught was just to cross multiply. But I like for us to understand why we're cross multiplying. So on the left hand side, we've got 2k times 2k. That's going to be 4k squared. And we're going to set this equal to, I guess I've got a FOIL here. 21 times k is 21k minus 21 minus k squared plus k. And as I was setting up this lesson, I realized that we hadn't really done a whole lot of factoring or solving quadratic equations at all this year. And so what I wanted to do was to go over how to do that real quick. So when you're solving a quadratic equation, you want to get it equal to 0. So let's see. I'm going to bring all this stuff over. That's just the way that Mr. Price likes to do this. So I'm going to say plus k plus, and that's k squared, excuse me. So that's going to be 5k squared. That's going to be a minus 22k when it comes over, and then plus 21, and we've got this equal to 0. And so with that, we want to go ahead and factor this thing right here, because we've got a quadratic equation. So if you'll remember from Algebra 2 last year, the way that you solve a quadratic equation is you've got to either use quadratic formula or you've got to factor it. I'm going to opt for factoring here. So 5k squared minus 22k plus 21 equals 0. What we're trying to do here is we're trying to find numbers. 5 times 21 is 105. That multiply to 105 and add to negative 22 here. And this is why we did the bell ringer for today, factoring a couple. So when you get to this point, you're not like, oh crap, what do I do? How do I factor again? It's been so long. So let's see, numbers that multiply to 105. We can do 5 and 21, but that won't give me negative 22. We could do 15 and 7. And if I make both of those numbers negative, those will work. And what I can do is rewrite this negative 22 right here with those numbers. Negative 15k minus 7k plus 21 equals 0. And really what we're doing is the distributive property in reverse here. So So what I can take out of both of these things, I can take a 5k. When I divide that out of both of these, 5k squared divided by 5k, that's k. Negative 15k divided by 5k is minus 3. The number I can take out of both of these things, negative 7k and 21, I'm going to take a negative 7 out, and that's going to leave me with k minus 3. Man, I love factoring. Things always work out so well. The k minus 3 here, that's our first factor. I'm going to factor that out. K minus 3 equals 0. The other factor that we've got here is 5k minus 7. Now, what we were trying to do here was find values of k that would make that sequence geometric. Don't forget what we were trying to do here. So this one's real easy. We say k minus 3 equals 0. So one value that's going to work for k is 3. And then the other value, we're going to set 5k minus 7 equals 0. So that means 5k equals 7. So then that means that k is going to equal 7/5. And what we're going to do real quick, I'm just going to show you all that works, that is indeed a geometric sequence, because I would be remiss if we did all that work just to not see the fruits of our labor. So we said k minus 1, and you can feel free to write this down or you can feel free to not, but I just want to prove to you all that what we just found is in fact a geometric sequence. So if we punch in 3 for k, so I guess we can make a mini little table. That would give us 3 minus 1 is 2. 2 times 3 is 6. And then 21 minus 3 is 18. And you can see we've got a nice little geometric sequence here where we multiply by 3 each time now. So then if we punch in 7/5, 7/5 minus 1 is 2/5. Let's see, 7/5 times 2 is 14/5. And then 21 minus 7/5, That's going to be, let's see, 21 minus 7/5. 21 times 5 is 105, so that's going to be 98/5. And we're multiplying each time over here times 7. So just to show you all, hey, that is in fact a geometric sequence. You're probably like, Mr. Price, that was whack. What is going on here, man? They're not. It's not all that bad. So hang with me here for a second. So the next thing that we're going to do is very, very similar example-wise to arithmetic ones. So if I give you different terms in a geometric sequence, we want to be able to write a general term here. So as a reminder, that general term is that the nth term, you find it by doing the first term times the ratio to the n minus 1. So we need to figure out first off what the ratio is, and then we're going to figure out what the first term is here. So to do that, what we got to do first is figure out what r is here. So we've got that the second term is -6. We've got the fifth term is 162. And to get from this second term to this fifth term, I want you to think to yourself real quick. How many times am I going to have to multiply by r to get to this 162 right here? How many times am I going to have to multiply by r? So to get from the second term to the fifth term, think about how many terms away those are. So we got 3, we've got 4, we've got 5. So we're going to have to multiply -6 times r to the third power to get 162. So what we're going to have to do is say, okay, well, let's solve that equation for r. So when we're solving that equation for r, we're going to divide both sides by 6 to get that r to the third is -27. So then to solve that there, we've got to take the cube root of both sides. And now to do that, if you're ever like, man, I can't find something, a lot of times it's stored under math. If you go to math, right where we did the fraction earlier, if you see right there, the fourth, where it says the cube root, we're going to take the cube root of -27. So the rate here that we're multiplying by is -3. And so what we can do is say, okay, well, I know that we're multiplying by -3 here. I know the second term is -6. So to put that simply, so -6 is the first term times -3 to the 2 minus 1 power. Well, that's just u1 times -3 equals -6. We're going to divide those by -3 to get that the first term is 2. And you're probably, Mr. Price, I looked at that thing and I knew it was 2. Awesome. But I like to promote some fluency, to kind of make you all think about, okay, that's why this formula works the way that it does. So the general formula here, the general term, the explicit formula, we're just going to say is the nth term. You're going to find that for this sequence by doing 2 times -3 to the n minus 1. To the n minus 1. So really, not so far, nothing too bad. Nothing too bad at all. And so with that, I'm going to show you all how to look at sequences on the calculator to kind of make predictions, to state things. And we're going to be using the calculator a lot the next couple of problems. So I'd make sure you have it handy. So we've got this sequence here. We've got 6 square root of 2 is the next term. 12 square root of 2 is the next term. And so the first, we want to know when this is going to exceed 1400. And so to do that, we've got to first off write a general term here. We've got to write a formula for the general times r to the n minus 1. So to do that, we're going to say, all right, well, the first term here is 6. And then look at this and think to yourself real quick. What is it that is getting multiplied by? What do we multiply 6 by to get to be 6 times the square root of 2? And hopefully you're like, well, to get from 6 to 6 times the square root of 2, you just multiply by the square root of 2, and we got n minus 1. And I do want to remind, students will fall into the trap of just not recognizing that that square root of 2 has value. So like the square root of 2 is 8.45 whatever, and if we multiply that by the square root of 2, we will get to 12, and so on and so forth. And so so our general form for this right here is 6 times the square root of 2 to the n minus 1. And so one of the things that I want to show you all on a calculator, if we want to know when is this going to exceed 1400, we want to know if we punch in a value, when is it going to exceed? What we can do is that if you will go into y equals, we're going to punch this function in. No functions were harmed in the making of this video, but we are going to punch it in. So we're going to say 6 times the square root of 2, and the calculator doesn't really have an n that we can use. It recognizes x better. So we're just going to say to the x minus 1. And what we're going to do is we are going to look at this function in a way that we can try to display all of the values. So when the people who made these calculators made them, they were like, all right, well, it would sure be nifty if you could have a table of values that you could list everything out. And sure enough, if you look at table here, right there, that's something that will let you look at these different values. And you can scroll up and you can scroll down kind of quick. But if your table looks funky, what you can do is you can hit second, and what'll light up right there is the little table set. So we're using table, and to set your settings, you're going to hit second, table set, which stands for table settings. And so you can pick where it's going to start. So I'm going to just start from 0. And then this delta here means the change in table. So how much is it going up or down? And then if you hit table, well, let's see. So there's 0. So this scrolls up real fast for me. I don't think regular calculators scroll up this fast. So we want to know when, if we pick these values of x, when it's going to exceed 1400. And let's see. So it looks like the 16th term is right before it. So we actually exceed 1400 there at the 17th term here. So U17 is 1536. U16 is 1086.11. And so we're going to say, so it exceeds on the 17th term. And we're going to talk about here in a second why it's so important to know this about a geometric sequence or series. There are some things that go hand in hand with it as far as those sequences are concerned, and we're going to look at those here in just a second. But we can use a calculator to look at that and to evaluate when it's going to cross certain thresholds. And this leads us in perfectly to our next section here, which is growth and decay. And so with growth and decay, these are both types of geometric sequences where we multiply by a percentage the entire time. And so some of the things that you can model with real world situations with growth and decay, you can do population growth, you can do radioactive decay, you can also do interest rates on money. We'll get more into that next semester. But there's a lot of real world applications for these geometric sequences. And so with that, we've seen U1 up to this point. In the formula for growth, you're going to see it as U0, because when you're dealing with real world situations and time, U0 typically stands for time zero, which we allow for in real life situations. It works the same as U1. And so with our formula for growth here, we've talked about this a little bit in other lessons, specifically with the variation. So we've got the nth term is we're going to do U sub 0, the quantity at 0, times R. Now the thing is with R, if it's growth, you're going to add the percentage to 1. If it's decay, you're going to subtract your percentage from 1. And we're going to put that to the nth power. To the nth power there. So largely looks the same as decay, as the geometric sequence, except we use U0 instead of U1, and then it's just the rate to the nth power. So we're going to look at 2 examples of growth and decay, and then we will call it a day today. And so the first one we're going to look at is the initial population of rabbits on a farm was 50. And the population here increased by 7% each week. And we want to use that to try and predict how many rabbits would be there after 15 weeks or after 30 weeks. And so to do that, what we're going to say is, okay, well, to figure that out, we're going to say that the nth term, I messed this all up. We're going to say that the nth term is, we're going to take the original times the growth to the nth power. So let's see here. If we're going to find U15, we're going to do the original here. So this 50 here represents our original population. So we're going to say 50. And if it's growing by 7% each week, that means we're going to be 7% above the whole percent. So it's going to be 107%. And if you want to know, like a easy way to remember that, percent means divide by 100. So if you want the decimal equivalent of something, if it's like 107 out of 100, that's going to be 1.07. We're adding 0.07 to 1. So we're going to say 1.07, and that's going to increase 7% 15 times there. So when we write that expression out, we're going to say that week 15 is equal to the original population, and that's increasing 7%. 15 times there. So I'm just going to punch that into my calculator because I'm not going to front. I have no idea what that is. So let's see. That is approximately 100. We're going to round that up. These are whole rabbits. You can't have 0.95 of a rabbit here. So we're going to round that to 3 sig figs there. We're going to do the same thing for the other one. So if you want to do that real quick, I'm sure you can. So we're to find week 30, we're going to do 50. It's going to increase 7% 30 times. These rabbits are getting out of control. We're going to say 50 times 1.07 to the 30th. And now, if we round that to 3 sig figs, 380, that's going to round up to 1, 381 wabbits. These things are getting out of control. And so, if we want to answer, it's important when you're talking populations, whether it's the population of Lexington, of a city, of an animal, it's important to know when you're going to reach certain thresholds, because I'm sure, I don't know what the number is, but if Lexington hits a certain amount of people, things will get scarce. Same thing with rabbits, same thing with any species of living thing. So it's important to keep tabs on these things. So we are interested here in how long it will take for the population to reach 500. So if we write out generally what that formula is that we were using, it was 50 times 1.07 to the n. And what we're wanting to know here is we're saying that the nth term is 500, and we want to know what value of n is going to make this work. And so what we're going to do for this is we are simply going to look at this on a graph. And so what I'm going to do is I'm going to say, okay, I'm going to take this general model right here, and I'm going to say 50 times 1.07 to the, I'm going to use x instead of n, and I want to know when that's going to hit 500. And we're not using a table this time because we want to know exactly when it's going to hit 500. We don't want to know a roundabout time. We want to know exactly because we're talking about time here. And so I'm going to pull up a graph of this thing real quick. So if you graph this thing and it doesn't look exactly like mine does, if you need to adjust the window right there, if you hit second and window and you're like, all right, well, we're talking time here for x. So the minimum I want to be is 0. Let's go to 20 and count by twos. With the rabbits, the starting population we said was 50. We're looking for 500, so let's go to 600. And what the scale here, what would be a good scale? I'm going to say 50. So then let's pull a graph out, and this is where I like the phone calculator better than the actual calculator. So I apologize if you got a TI-84. We're looking for the intersection here, and the thing is, on the phone, you literally just say, boop, there it is. I think it's so freaking cool. It's even got the bullseye there. I was fired up when I figured out you could do that. So the intersection there is 34.0 years, because we're rounding to 3 sig figs now. Stay woke on the sig figs. Now, if you're on a TI-84, the calculator steps, I'm doing this from memory, so you'll have to shoot me an email or Zoom me if I'm wrong. I believe you do second, trace, intersect, and then if you move your cursor, or in Algebra 2 last year we called it blinky dot, move cursor to the intersection and hit enter 3 times. And then enter, enter, enter. So that's how you do a intersection if you're not using that phone app there. I'm doing that from memory, so again, please tell me if that is wrong, and I can figure it out. And so we're going to look at one more example here, y'all. I know these are a little bit on the longer side today. Bear with me here. We got one last one about decay. We talked about growth. We got to talk about decay. So the scene here, we've got each year a physicist measures the remaining radioactivity in a sample. She finds that it reduces by 18% each year. If there was 1.52 grams of radioactive material left after 4 years, we want to know the initial quantity of the radioactive sample, and we want to know when it will hit 0.2 grams right there. So to find that initial there, we're going to try to set up our general formula here real quick. So we're trying to find U1. And the rate here, if we're talking about the rate, let's think to ourselves real quick. If something decreases 18%, think to yourself, what percentage of its value does it have left? If you lost 18 points on a test, what'd you get? So that is what, 82? And that 82% that's left out of a 100 total is 0.82. So if you multiply something by 0.82, it decreases it by 18%. Or you could do 1 minus 0.18. Either way, you'll get there. And so we're multiplying by 0.82. And I wrote U1, excuse me. That should say U0. So one of y'all is probably shaking your head right now. It's all good. So we need to figure out what the original term was here. And to do that, we can use this little factoid. They tell us it was 1.52 after 4 years. So U4 here, well, the way that we can write that is that the fourth term was 1.52. So we're going to say, all right, well, 1.52 here. We want to know this, so that's going to stay blank, times 0.82 to the fourth power. And all that we've got to do to find the first term there is get rid of it. It's multiplying here. So we're going to divide both sides here by 0.82 to the fourth power. And that should tell us the original amount here. So let's see. 1.52 divided by 0.82 to the fourth. That's going to be 3.36. Again, we are rounding to 3 sig figs now. Stay woke on the sig figs. We go to 3 of those bad boys in IB. So 3.36. And so we have figured out that that is the original amount of radioactive material. Spoiler alert for some of you all, that is how we figure out how old some of the stuff on Earth is. Some good old carbon dating, looking at half-lives and radioactivity of things. So now I'm done spoiling things. The last thing for today, we want to know how many more years is it going to take for this radioactive material to reduce to 0.2 grams. Reduce to 0.2 grams here. And so what we're going to do again is we're going to write out this general formula, 3.36 times 0.82 to the nth power. And we are going to say, okay, well, let me think here actually. Actually, you know what? Since we're doing how many more years, that we need to go from year 4. We need to go from year 4 here. So we're going to do UN equals 1.52 times 0.82 to the n, and we're going to set this equal to 0.2. I apologize about that, you all. I am just a little sleepy, but you know what? We're going to finish this out strong. So we got 0.2, we got 1.52, and we got times 0.82 to the x there. And again, I'm going to have to mess with my window. My numbers are way too large now. The starting number here was 3.36. We'll start at 4. We'll go to 0. We can count it by like 0.25s or something. Except that needs to be y values. What is Mr. Price doing? 0. We'll go to 20 and count by 2s. 0 to 4 and we'll count by 0.25s. Now let's see what this graph looks like. So you can see those things intersect right there. And so it asked how many more years. So 4 years have already gone by. So after that many years, so I guess from the original sample it would be, so we're going to say 10.2 years here. And from the original, it would have been 14 years total. But since it wanted to know from that 4 years, that's what we're going to look at there. And so that wraps up geometric sequences today. I apologize for this going so long. It wasn't my intention. In my head, I was like, oh, this is going to go so quick. But there was a couple things we needed to review, a couple ties I needed to make. So if you all have any questions on what we've gone over in these notes, please let me know. Please schedule a time with me on Zoom, and we can get it ironed out. I promise. We've got a couple more days left in this semester. Let's make sure we are finishing out strong. If you all need anything at all, please let me know, and you all have a good rest of your day. Bye.